Yeah, thank you for the introduction. Thank you for inviting me. And besides thanking the organizers, I would like to express my special thanks to Julia Göller, Robin Tress, and Karin Schelken, who have done an important work on getting these simulations to run and allow me to show that. So a brief introduction for why we care about magnetic fields and what we can learn from them. These are observations by Andrew Fletcher from M51, where we can have 2 points that we should take away here. One is the structure of the magnetic field, which orients mostly along with the magnetic field orientation and the spiral arms. And if we look at the magnetic field strength, we see relatively strong magnetic fields of the order of 10 microgauss or above, with some caveats on how you derive these magnetic field strength, but we have to deal with something of the order of microgauss fields. If we now switch the point of view and place ourselves at the position of the Earth and look around us, then there are two other things that we see in terms of the magnetic field. Here you see the dust emission and polarization. You see here in those streamlines how the magnetic field is oriented. In the disk region, you see strongly tangled magnetic fields. In the regions above and below us, we see rather large-scale coherent fields. And finally, the Faraday rotation measure, as we heard this morning, allows us to combine along the line of sight the integral of the number density of the electrons and the line of sight magnetic field. And I will come back to that in the context of the simulations. So if you would like to have a look at these things in simulations and we would like to compare it to the Milky Way, then one important thing is to have a Milky Way-like galaxy as close as possible to the actual Milky Way. So this is done in so we call them REA simulations in the context of the ERC EcoGal grant, where we put in as much physics as we can. I would like to highlight a few things. So very important is that the galaxy evolves in an environment that has the critical parts of the Milky Way. This is in particular, of course, the correct mass, but then also the individual components that change the potential of the gas or the potential of the galaxy. So in particular, the galactic bar and spirals are an important component that we would like to include. We use AREPO to do that. We try to do the chemistry as accurate as possible with a non-equilibrium chemical network. Then we have star particles that form individual massive stars. We account for the lifetimes. And for the feedback, we have supernovae and in the new iteration also radiation. And we include cosmic rays in a simplified gray approximation. So I would like to show you the evolution of one of these galaxies. Initially, we put in a very weak magnetic field and let the simulation via the dynamo grow the field to the field strength at the end. We run the simulations for 2 gigayears, and what you will see initially, there's no magnetic field or very weak magnetic field. You get a burst of star formation that pushes some gas out. If you wait for a bit longer, then the additional cosmic ray energy helps lifting more gas out. You get a dense and a smooth CGM with warm outflows, as we know that from cosmic ray-driven winds. And at the end, we also evolve a magnetic field that is comparable to what we expect from observations. So here you see a time evolution of 2 gigayears of the magnetic field strength. Here's one simulation or two simulations where we already start with a decent magnetic field. So here we start with a microgauss and that grows slowly to like 3 microgauss in the disk patch that I analyze. And here you see the simulation with the low magnetic field. We see an exponential growth, as we heard from Mordecai, corresponding to the small scale dynamo. Then it is taken over by the large scale dynamo and increased to comparable values. Here's an illustration of the magnetic field strength. We reach the 10 to 30 microgauss in the dense patches of the disk. And we see that the field, in the field lines here, is patchy and tangled in regions where we have supernova-driven bubbles, and in regions that are more quiescent, we see large-scale fields with large correlation length. Okay, let's now quantify this structure a bit more. Here I show you two different evolutionary stages at 1.5 and 2 gigayears of evolution. Here you see the absolute value of the magnetic field strength, and then here 3 projections in the toroidal component, the radial component, and the Z component out of the disk. So what you see is the toroidal component dominates, as we expect. The radial and Z components are mainly fluctuations and occur in regions that are related to local bubbles. I will come to that in a second. Another thing that is striking in the simulations is that we have blue and red regions here. So this is the projection along phi. So we see regions that are retrograde and prograde with the rotation of the galaxy. Interestingly, these changes from red to blue occur in an entire ring in the galaxy and evolve over time. So we see this red patch grows to this size after half a gigayear, and if you look at further evolution, we see changes in whether the field is that way or that way.
Quick question, why no bar? You say you have the galactic bar?
Yeah. So in this simulation, I do not show the simulation with the bar because the bar has other problems. I'm happy to talk about that later, but I would like to have the simple effects first. Okay, so if we look at these transitions, we can also check what kind of physical process is likely to occur with that. And in order to see the first impression, I just overplotted the local supernova that occur within a time frame of 10 megayears over the projection of the toroidal field. And it's a pretty messy business, simply because one supernova alone doesn't do much. You have to have clustered supernova, then there's a time delay, and so on. But there's some indication. For instance, here from red to blue, you see that there are many supernova occurring here. In the blue region, there are rather few. So we need to do that a bit more quantitatively.
Do you choose when the supernovas explode, or is it random?
No, we have a criterion that tells us when gas is collapsing, that forms a star cluster. Within that star cluster, we draw from an IMF massive stars. Each massive star gets a lifetime attached, and after its lifetime, it explodes. So it's not by hand, it's a self-consistent statistical model. Okay, if I look at the radial change of B phi as a function of supernova rate surface density, then what we clearly see is that here at 400 or so where there are no supernovae, then we hardly get any change. If we are above a certain density of supernovae, Okay, I don't know my plot well enough, it's at 200. Okay, but we clearly see if we have enough concentration of supernovae, we see a radial change of B phi. So this is a correlation, and that's fine. We would like to investigate that a bit more and see the cause. What is first, and why is a change in the field orientation triggered? So in order to do that, we can envision two different scenarios. One is that we have star formation and feedback, and that triggers somehow a flip in the magnetic field. Or we can have the case that the magnetic field flip is triggered by something else, an instability or whatever, that causes the compression of gas or the loss of local magnetic support, and that triggers dense regions and star formation. And what I did now is I looked at a snapshot and investigated whether feedback that happened 1 or 2 or few megayears prior to my measurement time has something to do with the magnetic field flap, and vice versa. I take the field flip and check whether 1 or 2 or a few megayears later I see enhanced star formation there. So first, as to understand that I understood the problem right, I did a proof of concept check with regions that have no star formation at all. So here you see a normalized histogram with of the absolute orientation of B phi. So if that is 1, we're either in the plane prograde or retrograde. If it's 0, then the radial or the Z component dominate. The regions without star formation and without supernovae are the solid lines. You can hardly distinguish them, and it's clearly the case at this. Most of the regions here are really in the plane, so correspond to a magnetic field in the plane. If we have star formation and feedback, moderate or strong, we see that the curves systematically shift. Okay, let's now do this in more detail and look at the distribution actually for supernovae at the measurement time minus 1 megayear or 2 megayears, and the star formation at time plus 1 megayear or 2 megayears. So what we see is that for the supernovae, the distribution is very flat with a small enhancement here. If we look for star formation, we see a very similar distribution but with a stronger peak here. So the distributions are not terribly different, but I have 200 snapshots, I have 10 million cells per snapshot, I have many hundred million star data. So I did a KS test to see whether these distributions are actually different, and they are different. So there's a small hint, it's not dramatic, but there's a small hint that we really first have feedback, and that triggers then in the following a larger change in the phi component of the magnetic field. Okay, so now let's go back to the observational domain and see how we can compare that to the actual data. So I do rotation measurements here, as we explained or learned this morning. It's the integral over the electron number density, the magnetic field along the line of sight, and then you integrate along the line of sight. This is the magnetic field, this is the electron number density, and here is the differential contribution NE times magnetic field line of sight, and I put an observer here in the center. So if you are in the center and you look around you, you see all the little contributions that point away or towards you, so you see small blue and red patches. If I place myself here, approximately at the solar circle, then of course the pattern looks different. I see large-scale pattern of the magnetic field that goes away from us and that is coming towards us. And then if you are also at a point where we have a flip from prograde to retrograde, then you can imagine that you also see asymmetric patches from red to blue in the different corners of your point of view. So if I do that, then the question is, where do I place myself? Statistically, you could place yourself in a random position of the galaxy and investigate how your rotation measure all sky map looks like. And if I place myself in a random position, I see things like this. I can clearly see the midplane, and I see large patches of positive and negative rotation measure. That's not surprising. If I choose a random position in the galaxy, I'm likely to be in a diffuse medium, and a diffuse medium without specific enhanced star formation has a large-scale field in the toroidal direction, which gives me those large patches. If I now place myself in the center of a bubble, as we have in our local bubble, then suddenly the large patches are still there, but are superimposed by a lot of small-scale patches. So I looked at plenty of those plots and then made a qualitative analysis, a quantitative analysis in terms of the angular power spectrum. So here you see the angular power spectrum for random positions. Random positions are dominated by low L contributions. And if you go to bubbles, then you see much more the details of the shell of the bubble or the complicated turbulence around you, which means your spectrum peaks at higher spherical harmonic contributions. So if it's really the bubbles, then we would like to know, is it the bubble interior? Is it the bubble shell? Or is it maybe the surrounding of the bubble? Because it's not just a bubble, there's like something like a kiloparsec box with enhanced star formation or so. So what I do for my integration for the rotation measure, I choose different starting points for the integration. Here I start with 200 parsecs and integrate out to the end of the box or so. So we see the small scale patches in one of the bubbles. If I now increase the starting point of the integration to 500 parsecs, we see small changes, but not too dramatic. If I start at a kiloparsec, we start seeing larger changes. And if I start at 2 kiloparsecs, I really change the major pattern, in particular at large altitudes. So that tells me between 1 and 2 kiloparsec from the local bubble is where the magic happens, in particular here. Now the problem is, we would like to have the full galaxy, we would like to run it for long, we would like to have a lot of physics in there, which means we have restrictions on the resolution. And we can't really trust our bubbles here, simply because of the limits in resolution. So that's why we went back to simulations of isolated boxes, where we resolve every supernova, and we were looking for local bubble analogs. And we found one, or several, but there's one that fits very nicely the energetics that we know from our local bubble, so 15 to 17 supernovae, also in a decent time range. Here is the density distribution of one of those bubbles. The streamlines here illustrate the magnetic field. And we did, basically, Ephraim Marconi did an analysis of where the rotation measure contributions come from. So he placed himself in the middle of one of these bubbles, shoot rays outward, and compute what is the differential changes to the rotation measure. So this ring is the same ring here, so this is a larger box, and you can nicely see the edge of the bubble where we start going into denser material and stronger compressed magnetic field correspond to strong changes in your rotation measure signal. That's in the XY plane, that's in the YZ plane, so you see our bubble is closed up here, is open here, and you see the strong contributions from the edge of the bubble. So this is fine, but it also has a few shortcomings. If we compare that directly to the Planck map, then I told you that we see the large-scale magnetic field here. If we have a small box that is not the full galaxy, we're obviously missing the large scales. So this is the small-scale simulation in the Planck view. You see a lot of structures, but if you look at the top and the bottom, you see small-scale fluctuations, contrary to the Planck map, which shows elongated streamlines, so large-scale magnetic fields. If we add a constant magnetic field on top of our turbulent magnetic field in the box, we're still missing the disk, obviously, but the polar caps now look more similar to what we see from the Planck structure. A bit hard to see here, but if you come closer, then you see that with the streamlines here correspond much better to the Planck map. So we have a large-scale model. That's fine in terms of large-scale dynamics. We have a small-scale model. Now we try to stitch that together and do everything in one go. And this is what we currently run. Unfortunately, I cannot show results because the simulations are basically still running. Robin Tress made a lot of effort in allowing us to do extra high resolution in the solar circle and the galactic center. And what we would like to do here is to actually follow a high resolution local bubble analog in the solar circle and then perform the same analysis, including a proper galactic center with high resolution. And with that, I would like to stop with some take-home points. So we see that the galaxy produces a toroidal large-scale field, as we expect from the dynamo. We see that there are localized magnetic field flips from prograde to retrograde. They are correlated with star formation, and there's a small evidence that it's actually driven by supernova feedback. If we look at the rotation measure, we see that we are dominated, or at least get significant contributions from the local bubble, which means we need to investigate this boundary much more. And that also tells us that we talk in the evolution about time scales and spatial variations that correspond to the evolution of the local bubble. Thank you.
Katja?
Okay, thank you. It's very interesting. I have many questions, but I will ask only one. When I look at the large-scale field, so you have these reversals, I would like to know what the field lines do. So let's say B phi goes from positive to negative. What does BR do? We know from the large-scale galactic dynamo that the ratio BR over B phi, so the pitch angle, has to keep the same sign. So you cannot have a field going this way, that way. So when B phi reverses, BR should also reverse. So the only way you can explain it is if you have a vertical field. So the field, goes up. Is it what you have, or what do field lines do? Yeah.
So, short answer: I don't know exactly what happens at these places because they all look a bit different. I have not done a full analysis of how the magnetic field streamlines actually look like in that regions. I still need to investigate. Yeah.
Next question,
so I have
Mordecai.
a somewhat similar question, which is, does the retrograde field actually, are there patches that come and go, or is it just a region that kind of grows and shrinks?
It's a region that mainly follows the star-forming rings.
So it kind of moves out.
And move out. I mean, in some cases they also come a little bit back, but it's basically correlated to the regions where we see enhanced star formation and feedback.
One last question.
Really cool talk. So I had just a question about the reversing field as well. Do you expect there to be a intense curl around this reversing field such that there is potentially just a current sheet that goes all the way around the galaxy?
I would expect stronger curls, but that goes in the same direction of it as Katja mentioned. I have not done a proper analysis of what the local changes all look like. Because you have a combined effect of not just rotating the field from one thing to the other, but you also have the expansion of the supernova remnants there. So you get the combined effect of an expansion of the bubble plus the rotation, the differential rotation, plus the flip in the end.
And are you sure that the current field configuration is a steady state configuration, or is it going to go away after more integration time?
It's steady state in a statistical sense that we do not get strong enhancement. So it's not in a growth phase, but yeah.
we have to move on. So let's thank our speaker again.